In this video, we will be describing the method for naming simple binary covalent compounds and a couple of our different organic compounds. There are a couple fundamental differences between ionic and molecular compounds, those that are held together via covalent bonds, which necessitates a different naming schema for our molecular compounds than for our ionic compounds that we have discussed previously. One of which is that ionic compounds, when we are reporting them, we use the empirical formula, which is the simplest whole number ratio of the different elements in that ionic compound. For the molecular compounds, we use the molecular formula, which tells us how many of each element are bound together to form a molecule. For the molecular compounds, because we're dealing with molecules, there is a set number, and we don't use the empirical formula. In the case of the ionic compounds, when we were trying to name them and figure out how many things are bound together, what we were looking at was the charge that each one of the metals should take and the charge that each one of the anions should take, and trying to balance out the charge to come up with an overall net zero charge. In the case of molecular compounds, the formula for a molecular compound cannot readily be determined from its constituent elements, because the same combination of elements may form many different molecular compounds, each with a different formula. If we're looking at just nitrogen and oxygen, they can form all these various unique molecular compounds: NO, NO2, N2O, N2O3, N2O4, and N2O5. In the case of NO2 and N2O4, the empirical formula for these two compounds is the exact same, right? The simplest whole number ratio would be take the N2O4, divide by 2, which would give you the NO2. What that tells us is that we can't use a naming schema that would rely on the empirical formula. So for our molecular compounds, we have a naming schema that specifies the number of each type of atom that we will find in our molecular compound. That naming schema relies on prefixes, which are used to designate the number of each type of element. We will be looking primarily at binary compounds, those compounds that contain two different elements, both of which, because we're talking about a covalent bonds, are both non-metals. So the prefixes we will use are for a number of 1, or one atom of that particular element, we'll use mono. For 2, it's di, 3 tri, 4 tetra, 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nona, and 10 deca. These are the same prefixes that end up getting used for our hydrates that we were talking about before, although we don't have the hemi, because they come in whole number combinations, and so we wouldn't have the 1/2. So again, mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca is what we will be using. So the general schema for naming our binary compounds, first is if it has a common name, we use the common name. So for water, which is H2O, we call it water. It is not called dihydrogen monoxide, it is just water. If a compound doesn't have a common name, then we proceed through the rest of our steps. First, we will count the number of each atom. You write the name of the element with the smallest group number first, so that which is most left on the periodic table comes first. If two elements lie in the same group, then you will write the element with the greatest row number first, so that would be the one that is below. The prefix given to each element will indicate the number of atoms that are present. We will put the appropriate prefix in front of the elemental name to denote the number of that atom per molecule. If the first atom has only a 1 atom, we will drop the mono prefix. So for example, we wouldn't have monocarbon dioxide. We drop the mono if there's only 1. For the second atom, we will again be dropping the ending and replacing it with "ide," similar to how we did with ionic compounds. So looking at a couple examples, N2O, we have 2 nitrogens, so it gets the di prefix, 1 oxygen, so it gets the mono prefix. So this would be dinitrogen monoxide, though this is also known as nitrous oxide or laughing gas. P2O5, we have 2 phosphorus, so it would get the di, 5 oxygen, so it would get penta, so this would be diphosphorus pentoxide. CO, we have 1 carbon, so you might think of it as monocarbon, but if the first atom is the one that has a 1, we drop the mono prefix. So instead of this being monocarbon, it's just carbon. We have 1 oxygen, so that's monoxide, so this would be carbon monoxide. For CO2, we have 1 carbon, so it's just carbon. 2 oxygens, so that's a di prefix, so carbon dioxide. NH3, it has a common name, which is ammonia. If it didn't have the common name, we have 1 nitrogen, so that is just nitrogen, 3 hydrogens, so this would be nitrogen trihydride, although because it has the common name, it is called ammonia. Last of our examples, we have 1 carbon, 2 sulfur, so this would be carbon di for the 2, and then sulfide. We will now try a couple additional examples. Please pause the video, try them out on your own. When you are done, hit play. So the names for these, what we will first need to do is figure out how many of each one of our elements we have. We have 1 carbon, so we just call this carbon. And then we have 4 chlorine. So we would call that tetra, and then chloride. T-E-T-R-A, and then chloride. So chlorine, get rid of the ene and change it to I-D-E. Carbon tetrachloride. The next one is silicon monoxide. So because the silicon doesn't have anything in front of it, we know that there's only 1. So we have silicon monoxide would be SiO. For our next one, we have a sulfur with 10 sulfur and 1 oxygen. So 10 is deca, and then sulfur, 1 oxygen. So that would be monoxide. Okay, next one, dinitrogen trioxide would be 2 nitrogens because of the di. And then tri tells us we have 3 oxygens. Last one, sulfur hexafluoride. Because there's no prefix in front of the sulfur, which is the first of our elements, right? So because that's the one that comes first, we know that it has a 1. Because if there's only 1, we drop the mono. So this would be sulfur, single sulfur, and then hexa is 6, so this would be hexafluoride. So this would be SF for our fluorine, 6, sulfur hexafluoride. The last thing we will be looking at is naming simple organic compounds. For this course, we will be considering only the following 10 hydrocarbons. A hydrocarbon is a molecule that contains primarily carbon and hydrogen. The ones that we will be looking at contain only carbon and hydrogen. They differ in the number of carbon atoms. They differ in the number of carbon atoms and hydrogen atoms that they contain. For the chemical that has 1 carbon, 4 hydrogens, so this would be a total of 1 carbon, that would be methane. 2 carbon, 6 hydrogen, total of 2 carbons is ethane. Then 3 and 8 would be 3 total carbon atoms, would be propane. 4 carbon atoms is butane, 5 is pentane, 6 is hexane, 7 is heptane, 8 is octane, 9 is nonane, and 10 is decane. So the naming schema for the simple organic hydrocarbons that we will be considering is based on the number of carbons. 1, we'll use a methane, 2 is ethane, and you can see from 5 on, we get the same prefixes that we've been using previously. Penta, hexa, hepta, octa, nona, deca, and then you have ane at the end. So pent-ane. So each one of the compounds that we will be working with have the end of an ane. If you've taken more advanced chemistry, you might know that these are alkanes, which are the compounds that follow the general formula of twice as many hydrogens as carbon plus an additional 2. So it would be CnH2n plus 2 is the general formula for an alkane. So in terms of figuring out how you will name them, if it's more than 5, you use the exact same prefix that you've been using before and add ane. The difficulty is with the first 4, the methane, ethane, propane, and butane. The prefixes are meth, eth, prop, and but. Essentially, for this series of compounds, it just comes down to memorizing which one you are working with.